Here we have a light ray passing through medium A. It hits the interface for medium B and is refracted. Suppose the light ray passes through this point P and we want the light ray to pass through this point Q in medium B. By the principle of least time, it is a fact that the light ray will follow a path that minimizes the time taken for it to go from P to Q. Let the speed of the light beam in medium A be CA and the speed of the light beam in medium B be CB. Let's suppose that the path of the light ray that minimizes the time taken for it to go from P to Q cuts the interface at this point O, which is a distance x from a point directly below P. Since the light ray is assumed to travel at a constant speed in medium A, the time taken for the light to go from point P to point O is the distance of P to O, which is PO, divided by the speed of the light ray in medium A, which is CA. So distance divided by speed gives us the time taken, and the time taken for the ray to go from O to Q is the distance OQ divided by the speed in this medium, which is CB. Now we can get this expression in terms of x. A and B are fixed because remember points P and Q are given to us. They're fixed points. We can use Pythagoras' theorem to get PO in terms of x. It's the hypotenuse of a right angled triangle of short sides A and x. So PO is the square root of A squared plus x squared. Now what about OQ? Let the horizontal distance between P and Q be small d. Okay, that's a constant, that's a given, since P and Q are givens. So if we look at this right angle triangle here, we can see that the horizontal side of it is d minus x, this distance here. So we have to square the two short sides of this right angle triangle. So here's the picture. We get b squared plus d minus x squared. Square them, sum them, and take the square root, and that's the distance of O to Q in terms of x. And we divide that distance by the speed of the light in medium B, which is CB. So the only variable in this is x. X is what we have to determine. A, B, D, CA and CB are constants. So remember, by the principle of least time, the light ray will follow a path from point P to Q that minimizes the time. So we want the value of x that minimizes t. So to do that, we need to differentiate t with respect to x, set the derivative equal to 0. So let's look at t of x and let's differentiate it. Well, we use the chain rule. Take the half down, subtract 1 from a half to get minus half, then multiply by the derivative of what's inside the bracket, which is 2x. Remember, a is a constant. So we do the same here. We take down the half, take 1 from a half to get minus a half, and multiply by the derivative of what's inside the bracket. So let's differentiate what's inside. Well, b squared is a constant, we get 0 for that. Let's look at this here. Now we can use the chain rule on this thing because we have a function of x inside. So we get 2 times d minus x to the power of 1. We just differentiate around the brackets. Now we differentiate what's inside the bracket to get minus 1. And all of this is divided by CB. Now this term can be brought down and the 2's cancel. Over here we can bring down this term as well. It's to the power minus half, bring it down. We raise it to the power plus a half. We can cancel the 2 here. And we multiply minus 1 by d minus x to give x minus d. So we want to set the derivative dt dx equal to 0 and solve for x. Once we know what x is, we will have the path of the beam fully specified because we know what a, d, b are. We can shift this term over to the right hand side and we just minus what's on top to get d minus x. Let theta A be the angle of incidence of this ray and theta B be the angle of refraction. Notice that this angle here is the same as this angle. These are called z angles because the normal here is perpendicular to the line through P here. So in this right angle triangle, sine theta A is opposite over hypotenuse. Side opposite theta A is x and the hypotenuse is OP. So sine theta A is x over root a squared plus x squared. So we can replace all of this thing here with the sine of theta A. Now here we have a pair of z angles. Again, this is theta b. The sine of theta b is opposite, which is d minus x, over the hypotenuse, which is OQ. And that's exactly what we have here. So d minus x is the opposite and OQ is this square root quantity. So we can replace all of that with sine of theta b. So we'll end up with sine of theta A over CA equals sine of theta b over CB. If we rearrange this equation here, we get sine theta A over sine theta b equals CA over CB. So the sine of the angle of incidence divided by the sine of the angle of refraction is equal to the speed of light in the first medium, medium A, divided by the speed of light in the second medium. And this ratio of the speeds of light in the two mediums is the refractive index of the medium. Now for this picture here, we can see that theta b is less than theta A. So the sine of theta b will be less than the sine of theta A. Remember, as theta approaches 0, the sine of it will also approach 0. So what does that tell us here? Well, it tells us that this fraction is greater than 1. So that means that CA is greater than CB. So that means that the light is traveling more quickly in this first medium and it slows down. And when it slows down, the light ray is bent towards the normal. If light traveled more quickly in medium B, then the light ray would be bent further away from the normal. So the angle of refraction would be greater than the angle of incidence.